Hi, kids. Hey, I'm here at school, and I'm making this movie because you're not here. So, I am going to make a movie talking about parallel plates and equipotential lines and a little bit with electric potential energy and maybe electric fields, and it's going to be amazing. So let's talk a little bit. So here, let me explain you the setup. So here is my setup. So I have two parallel plates here. I have a positive plate. This is attached to my power supply. I have a negative plate. It is also attached to my power supply. Let me show you. I have my voltmeter here, which you can see. I am going to hold this to one plate and this to the other plate. And you can see that the voltage, hang on, is, hang on. What? Come on. We'll go to there. You know, the voltage is just under 70 volts. Okay. Let me see if I can actually get it so it is 70 volts. All right, so 68 volts. There we go, 70 volts. We're going to say 70 volts just because 70 is a nice easy number, but you can see. So it's varying a little bit, but there's roughly 70 volts from one plate to the other. So here's what this means. If the potential difference, the voltage difference is 70 from here to here, that is meaning that you can think of it like this. If this is the positive plate, this would be positive 35 volts. This would be negative 35 volts, okay? And then in between here, if you were to think about how is the, you know, the equipotential lines and stuff like that, we'll talk about that. It is roughly 35 centimeters from one plate to the other. So we're going to say it's 35 centimeters. So we're going to have 2 volts per centimeter in between here. Okay. So let's pretend that I have a proton. It's just a marble. We can pretend. But this thing has, we'll say it's just some object with a positive charge. If this thing has a positive charge, where would I want to put it so it has the most potential energy? That's right. Pause it and figure it out. Pause it. Okay, hopefully you came back. And then hopefully you didn't say, well, put the positive charge over here because then it wouldn't have hardly any potential energy. You would want to put it on this side, close to the positive plate. Well, if you put it close to the positive plate, then yeah, this charge would have lots of potential energy to get converted to kinetic energy, going from there to there. And if you wanted to, you could find how much energy it has by doing the change in energy, which if it moved from this plate to this plate, the change in voltage would be 70 volts, and then you can multiply that by Q, and then you could figure out how much your change in potential energy is, okay? If you wanted to talk about equipotential lines, so lines that have the same voltage, well, if I wanted to put my hand in so there's no voltage across my hand, so if there's a voltage from here to here, charge is going to move through there. And if I don't want charge to move through my hand, should I put my hand in this way or should I put my hand in this way? This way or this way? So again, pause it and talk. Okay. Pause it. Did you pause it and talk? Yeah, pause it. Okay, so we're going to figure this out. So if I don't want charge to go through my hand, I have to be on an equipotential line. Well, if this is a parallel plate and this is a parallel plate, the equipotential lines are going to be like this. So I could put my hand like this, like this, like this, like this, like this, or any place in between as long as I am parallel to the different plates. So let me demo that for you. So I'm going to put my hand, it doesn't matter where I put it in. So ready? I'm a little nervous. No! Just kidding. There's actually no charge, okay? So I'm on an equipotential, okay? On an equipotential line, on an equipotential line, on an equipotential line, no charge there, okay? But if I want to get zapped, okay, if I put it like, ooh, that was a good zap. If I put it like this, then I get a zap, okay? If I want a bigger zap, I would have to put my hand, ooh, that's a bigger zap, farther apart. If I want a smaller zap, I would have to put my fingers closer together. Remember, there's about 2 volts per centimeter. So if I go 10 centimeters, this is 10 centimeters. Then if there's 2 volts per centimeter, there's roughly about 20 volts, if I go like this, there's roughly about 20 volts between my fingers. So then the charge is going to go through my hand, and that's why I get a little bit of zap. So if I wanted to show you that, if I was to say roughly 10 centimeters, that's probably roughly 10 centimeters. I guess pretty good. You can see that was 18, so that's going to be closer to 10 centimeters, okay? Because there's 2 volts per centimeter. Does everybody, hopefully that makes sense? And remember, you know, like if I was to go that same distance, you know, so it's there, and I was to go the same distance here, it's going to be this about the same, and the same distance over there, it's about the same, because I'm moving a little bit, but you get the idea. That, you know, shock here, there is all going to feel the same. If you had to map this, okay, that if this is positive 35 and this is negative 35, well, hopefully it makes sense. 0 would be right in the middle, okay, and then maybe like if this is halfway, half of 35 would be 17.5 volt, negative 17.5 volt equipotential line. So it's like, well, this finger's at negative 17.5, this finger's at negative 17.5. What's the potential difference? Oh yeah, nothing, okay? Hence, no charge would move through my hand that way, okay? The water looks kind of gnarly just because, I know gnarly is a good word in it, that it looks kind of gnarly because remember, pure H2O is a good conductor, so I want it, or sorry, is a terrible conductor, so I put some impurities in it to make it a better conductor. All right, so hopefully that makes sense. Let's talk about it in terms of this. So I want to show you this. So I have a table here, okay, and here's my thought with the table. So let me show you guys this at the right level. Actually, you know what? I'm going to pause, and then we'll come back for the table part. All right. Bye, kids.